Okay, good afternoon, everybody. I hope everyone's having a wonderful day. It's Friday already. So we're going to be moving on to something brand new, but it also will feel very much something that you've seen before today. So we're going to start talking about, this is effectively the final chapter of this course, if you want to think about it in terms of chapters. We're going to talk about intractability and complexity theory. So today is dedicated to really me giving you the kind of the fundamentals. So whether it's been that you've never seen big O notation, or it's been the case that you want to see some examples of how we can measure the running time in the worst case for an algorithm. We're going to be looking at this from the context of Turing machines today. And I'll also be drawing on a parallel between something you may have seen in a course like 340 and the stuff that we're talking about here. So you have a very natural bridge to take anything that you've learned from a previous CS course on algorithm analysis and adapt it to the theory that I'm talking about here. So you'll find very much because of that, I'm going to be going from varying degrees of granularity. When I say that, I mean, sometimes I'll talk about specifically a Turing machine. Sometimes I'll talk about an algorithm, more in a pseudocode-esque way that you may have seen in a previous kind of class, wherever it's convenient at this stage. But today I'm mostly focusing on just Turing machines, because that's why I need to make sure I exactly define a lot of things here for you, okay? So that's why. I want to make sure I formulate everything to you to an exact T, okay? So that when you walk out of this class, you can define exactly these things. So here's the main idea and where we're going to be going from here. So up to this point, we've been looking at languages and problems from just simply, does there exist a Turing machine that recognizes or decides that language, depending on what we're interested in doing. Typically, we're interested in decidability or undecidability. What I want now is I want to be able to look at things more from an efficiency standpoint. So instead of it being like, okay, can I do it? That's a much broader question. Now I'm going to narrow things down even further, and now I want to know about the efficiency of algorithms. So what I'm going to do is I'm going to introduce a clock to our Turing machine so that I can kind of measure how long they take. So what's this clock going to simply be? It's simply just going to be that I'm just going to count the number of moves or steps that happen for my Turing machine models. So that's really all it is. So here's the idea. So first, I'm just going to kind of recap something I've said previously, but I'm going to phrase it a little bit more carefully this time. So I'm going to talk about the time complexity of a deterministic Turing machine, so a DTM. So remember, I used this acronym earlier on in the course when we were talking about deterministic versus non-deterministic. So if I give you a DTM M and it halts on all inputs, so I'm going to presume that this is a decider, right? So we're going to call the worst case running time, which I'll colloquially use as just saying running time. So, and that's pretty common when we talk about algorithms anyways, is the running time or time complexity of M is going to be given by a function, f. So I'm just going to call it f here. I can give it different names. I'm just calling it f here for my definition. And it's going to take in a positive integer, and it's going to spit out a non-negative real number. And you're going to ask, okay, well, what is this thing? Well, sometimes people like to call this a growth function or a complexity function. I usually like to call it a complexity function, but there's a lot of different names for it. Now, you might ask, why does it map to the non-negative real numbers? Or you can even make that positive real numbers if you like. I'm just being very flexible with my definition just for our sake. You might ask, it's because I want to be able to have it so that my definition is really easy and broad to use. But you'd agree with me that the way I defined a move for you is simply an integer, right? Like it's based on, okay, there's one move that happens, then there's two moves, then there's some finite number of moves. It's always some integer number, right? So somebody might also present this definition to you where this is actually a positive or even a non-negative integer instead. So what the first input for f is going to be is actually the input length or input size, n, for our Turing machine. So I'll refer to this as a complexity function in this course. And f of n is going to represent the maximum number of steps or moves that m makes on any input of length n. So remember, we gave the motivation behind this earlier on in the course, where I talked all about how, yeah, no, like, we would like some way of talking about how efficient an algorithm is and how many moves it makes. In the context we talked about it before, we talked about the connection between different models and how many moves they make, right? So I'll give an example of us measuring the time complexity of a Turing machine in a little bit. But here's the idea. So imagine I give you a deterministic Turing machine. It starts off in some initial ID when we start off, instantaneous description, and it makes a sequence of moves. So what we're interested in is the maximum number of steps or moves that we can make. So what does that mean? Because it halts on all inputs, there's going to be some point where it's going to accept or reject. And the largest possible number of moves that I can make for any input n is captured by f of n, where n is going to represent the length of the input. So are we okay with this definition? Or any questions about it? So from more of an algorithm, like a higher level standpoint, you may know n as the input size. So usually it's called input size in that context. It's the same thing. It's just that usually when people talk about input size, they're talking about the encoding of all your input parameters. That's usually how it's used a little differently, but it's the same idea. And it makes sense if you think about it. Our input of length n, in that broader context, we usually would say it's the number of bits used to encode the input, which is effectively what we've been doing up to this point, right? So are we okay with this? Just give me 2 thumbs up if we're all good with this. Okay, so if that's the case, now I want to define for you the time complexity of a non-deterministic Turing machine, which I have not done. I just implicitly told you how the moves work. So let's head on over here. I'm going to shuffle my way over this way. Okay, so we're going to move on over here, and I'm going to define what the time complexity of a non-deterministic Turing machine, or NTM, is. Now remember, I gave you the definition of a non-deterministic Turing machine before. Remember, this is our Turing machine that has like clairvoyance, and it has the ability to have a whole set of moves that it can make. You could think of it as them happening all at the same time, but in the way that makes most sense for us when we're going to define this time complexity, we're going to think of the non-deterministic Turing machine as this clairvoyant machine that knows which paths to take. So here's the idea. So I'm going to consider the non-deterministic Turing machine to be a decider again. So I'm going to assume it halts on all inputs. I must stress that just like in my previous definition and this one, I rely on the fact that they are in fact deciders, right? Otherwise, the time complexity as I've defined it is infinite. It may be infinite because there may be some input for which it never halts, right? That means that the maximum number of moves possible may not actually be a finite number. So that's why we're doing this, because we're interested in the efficiency of our machines here. In contrast, and to be analogous with this, we're talking about the efficiency of algorithms. So the time complexity, or worst case running time, for our non-deterministic Turing machine will be also given by a complexity function. Remember, the n is going to represent the input length, and this will spit out a value for us that will represent the number of moves or steps that machine makes. In this case, our non-deterministic Turing machine. Now, one thing I must stress, in this lecture, you're going to see me abuse a bit of notation here. I'm just going to make a remark about this. So this is a very common abuse of notation. I'm not the only one that will do this to you. A lot of CS people like to do this all the time. And I know it frustrates some people, but it's very common. So when somebody describes you a function, usually they call it f, right? That's the name of the function, right? When somebody writes f of n like this, or f, depending on how you interpret this, when I write f of n like that, or f, when I write it like that, it's kind of confusing, isn't it? Depending on how you read it. Can somebody tell me why? Why that might be considered an abusive notation if I were to use that to say, okay, that's the function f given some input n. Is there anybody that could tell me why somebody might say that's an abusive notation if I'm going to use this to describe f? Come on, somebody's got to know about functions. What does f, like when I write it like this, what does this actually mean from a function standpoint? Is that the name of a function? No, right? It's the output of a function given n, right? Yeah, it's the value it has. Exactly. So just to be clear, when I use this, you have to always look at the context for which I describe it to you. So sometimes here, I'll be saying f of n, as in what's going to be roughly right here. But you notice the way I use it actually overloads it, meaning that I'm also talking about the function f. So very often you'll see me write something that looks like f of n, but it's actually me saying it's the function f, and I'm implicitly telling you what the input is for it. In this case, it's the input length. So just be aware of that. That's a pretty common abusive notation that I've seen mathematicians do it, I've seen computer scientists do it, but it's just a matter of shorthand. So just be aware when I write this, just be careful with the context. So just be aware of the context. It's just, it may be the name with input, or it could be a value. It's just a shorthand. It's technically an abusive notation, but it's a shorthand. I just feel like I wanted to make a remark about this. I'm sure that there's some people in this class that have already had that spiel given to them at some point. If not, I just feel like doing that for you, because I think it's important that you see that there's different ways people write functions out. This is one such example. So anyways, now back to this, because I wanted to just acknowledge that fact. So what's the maximum number of moves that a non-deterministic Turing machine makes? So let me draw you a picture, and I'll justify this last part here for you. So suppose I give you a non-deterministic Turing machine n. It will start off in some initial ID, and then it will have the ability to branch. It's a little squeaky marker. Ooh, that's a little squeaky. And you may recall this picture from a previous lecture when we were showing the equivalency, well, the computational equivalency of an NTM and a DTM. So I have it where I make a move, and I have a set of possible moves that I can make. Now, because it's a decider, some of these may lead you to a reject. Others may still continue to process. And somewhere down the line, one of these may actually accept. And however, it's very possible that there might be some path along this computation tree where it rejects, but it may happen much later on. But because it's a decider, you know every single path in this computation tree will eventually hit a leaf. Does everybody see that? This was not the case when I was talking about them more generally, because in the more general case, there could exist a path that runs on infinitely in my tree, where the path length there's no finite value it has, because it just keeps going and going and going. Which naturally represents a loop, right? Where we just keep having it happen over and over and over again. So you might ask, okay, so how do I know what the running time of my non-deterministic Turing machine is? Well, what you do is there's going to, because it's a decider, you know, regardless of what the input is going to be, you know it's going to halt at some point along this. It may halt here, it may halt here. Sorry, it may halt here, or it may halt here. It may halt on another branch where it's going to hit a leaf. The point is that if you look and try to figure out what the time complexity is of n, it's going to be depending on one aspect of the tree. It's the maximum path length, because that's the maximum number of branches that can happen on my computation tree. Which one of these branches will be a choice that the NTM makes, right? So naturally, when I talk about the time complexity, it's always going to be this maximum path length in the computation tree for any n. So are we okay with this definition of time complexity for our non-deterministic Turing machine? Are there any questions about this? Because if we're okay with this, I'll proceed. I'm going to switch markers. This one's a little squeaky. It's a little squeaky. Okay. If we're okay with this, why don't we proceed? So why don't we head on over here? Just for the fun of things, I'm going to do a strut over here. Just gonna walk my way on over here. So why don't we talk a little bit about how we're going to measure these things. Now, you'll very often find when we're analyzing algorithms, especially when we're dealing with Turing machines, we would like a nice simple way of writing out this running time. And I have to make sure everybody's on the same page. So I have a question, just for generally everybody. Has anybody in the class never heard or never seen big O notation before? Don't be shy about it. I'm going to give you a quick review just as a reminder. But it's good to know these things. It's helpful for me. So that way I know what sufficient detail I need to go into with this. Regardless, if you find yourself needing more I've seen it, but reviews are always helpful. Okay, good. So, if you ever find yourself needing more examples of big O notation, don't hesitate to reach out to me. I have lots of examples. So, here's how I'm going to define big O notation for you. Let f and g be complexity functions. So, as a fun remark, this is quite literally the same definition I would use in a class like 210 or 340. So if you've seen something like this, you're going to be well in place for this. So I have these two complexity functions. Then I'm going to define f is big O of g of n. I must stress that this is the mathematically correct way of writing this. However, computer scientists use a different convention very often. They use an equal sign instead of this. You can use either one of them right here. So this is just because big O dictates actually a set of complexity functions. It actually falls right out of the definition. So sometimes you'll find me using a set theoretic in. Other times you'll see me use an equal sign. In either case, you should read this as me saying is or is in, okay? So it's okay if you use the set theoretic in, if it's okay if you use the equal sign. Either one has its own purposes I'm going to mention in a moment. So f is big O of g. If and only if there exists constants c, which is going to be a positive real number, and n0, which is going to be a positive integer, such that for all n greater or equal to n0, so there's going to be some point, this is going to be n0, this inequality is going to have to hold. F of n is less than or equal to c times g of n. So this is the formal definition for big O. You may have seen this one in the past. If not, you're in for a treat today. So, just a couple of things. When it comes to proving claims involving big O, I'm not going to be doing any proofs here for this. This is something I would presume would be seen in something like 340 or in 210. I know those are kinds of classes I like getting students to prove these kind of things. But like I said, if you need examples, feel free to bug me. We'll just use the notation in this class, okay? I'll just presume you know what big O notation is when I'm using it here. You won't see me asking you to prove a big O claim on an exam or something. Just to be clear, I may ask you to use it though. So here's the game plan, very simple. There's going to be this constant c, there's going to constant n0, and there's going to be some point for which one of these functions is going to get dominated by the other by some multiplicative factor. Now you might ask, what is this c for? Because you might ask, okay, well, what means for one algorithm be more efficient than another? Well, there's a couple of technical reasons that I won't be able to get into, otherwise I'll spend like 20 minutes easily explaining it for you. But there's different ways we could actually talk about the Turing machines so that we can effectively artificially speed them up or slow them down based on a constant factor. But it effectively is analogous in some ways, it's not quite, to the explanation I typically will give students about general computers. So very often you'll have your elementary operations that you tend to measure with your Turing machine, or in our case, computer or Turing machine, where each one of those will have some CPU clock cycles. In our case, we count moves with our Turing machine. So what happens very often is you have it where each one of those has some CPU cycles if you were to think about it as an actual computer, like a real computer. And each one of those means it has some constant number of those roughly. So when you're adding up these operations that happen, in our case, moves on our Turing machines, what happens is it's going to be based on some multiplicative constants that are going to appear in the actual system. Now, in the Turing machine context, the way this gets reflected is actually based on how many states you use to represent different aspects of your Turing machine. So for example, I could give you a Turing machine, and there's a theorem that effectively allows me to say that if I use more states, I can speed the Turing machine up, or vice versa, or something along those lines. I'm not going to talk about that theorem here, but it's very much similar to the idea that you can have a machine where you can give it basically more power and effectively will speed up those operations. Or in our case, the execution of the algorithm. Or in our case, halting the Turing machine. But basically, if I had another month, I would easily show this for you. But it's I'm just trying to remember colloquially off the top of my head. I'm trying to remember the name of the theorem that's for this. But effectively, it boils down to that this constant factor is to allow you to make distinctions between machines that are artificially being boosted by state counts, or it is, in our case, like if we talk about an actual computer, like when we measure the running times of algorithms, those constants could represent the time it actually takes for certain operations from at a hardware level, like those CPU cycles on an actual computer. And each one of those may represent a specific constant, and different computers have different constants. For example, doing addition or subtraction or other things like this. But hopefully this gives you some justification of why this C is right here. This is just to make sure that when I count the operations for sufficiently large n, I'm indeed capturing what happens when I give you any arbitrary input n, which those can be very, very big. Some people would call that the growth rate of the functions and comparing the two growth rates. So there's a few different ways to think about this. But hopefully you find that explanation kind of helpful with why this definition is a thing. Is that you can think of these constants like some way that there's some difference between your machines in terms of the efficiency they may have at an individual level versus all fossil computers. And this N0 is to count for things such as trade-offs. So for example, one algorithm may perform very well for small inputs, but once it gets larger, you're going to find that we want some nice natural way of talking about this algorithm is more efficient than another for all inputs n. And this is how we're going to capture that, is that there's going to be some point where N0, where n is going to start having where this is going to hold. Okay? I just feel like I need to explain that, because it's often helpful for students when they're seeing this definition. It looks a little daunting. So, right, like I want to reiterate, we're going to very often use this equals notation here for the ease of informality. You're going to see in my examples why, but you'll just be aware that these two things from a mathematical standpoint really are trying to say the same thing. However, often we'll use the set theoretic in whenever I want to be a bit more implicit that I'm talking about a member of some set or class. Okay, so here's some, so just to be clear, so that's our definition of big O. We say G of n, we say G, gotta be careful, we say G is an asymptotic upper bound, for F. So here's some tips, just to make sure everybody's sort of on the same page when we're going to use this. So here's some tips. First, big O suppresses constants. So it suppresses constants and constant factors. So just as an example, so I'll give you two examples. So for example, if I give you 50n squared, this 50 doesn't matter. So I could always write it like this. 50n squared is big O of n squared. I could just get rid of the 50. Here's another example. So suppose I give you, say, let's go 3 to the power of n plus 2. We can always say that this is big O of 3 to the power of n. But you see, I could just not worry about the constants. In an algorithm analysis class, I'll typically prove properties like these for the students. But if you find yourself curious or find yourself not sure why, you can always bug me, ask me after, or send me an email. I'm very happy to talk about it. In addition, if F has several terms, that include constants, one can write F is big O of G, where G is the highest order term, now this marker's highest order term without constants. Let me switch my marker. This one is really unfortunate. Let's just, it's gone. So let's do a couple of examples. I just want to illustrate the notation, just to make sure everybody's on the same page here. So here's an example. Say if I have n plus n squared plus 3n cubed, I can tell you that this is big O of n cubed. I just take the highest ordered term. In this case, I have a cubic there, and then I get rid of the constants. You have to be very careful when you're doing this, though, because if, say, for example, you have a sum of a bunch of functions, and all of them actually have a closed form expression, you have to be very careful. With polynomials, you can get away with things like this. If it's something a little different than that, you have to be very careful and count them separately. So one other remark I want to make is about the informal use of big O. So just to be clear that there's this, if you want to be very formal about everything, you could talk about big O in terms of sets. So you could talk about, oh yeah, it's a subset and so on and so on. But I'll show you that there's a very useful way of talking about big O notation. So for example, if I gave you this right here, I could always write this as, say, n. Like suppose instead I wanted to talk about each one of these in terms of big O. Because you'd agree with me that n is big O of n, right? And you could say that n squared is big O of n squared, and 3n cubed is big O of n cubed, right? Sometimes I would like to have a very simple way of taking all of these and putting them all together. And this is where this equals-like notation is rather helpful. So notice that this technically makes absolutely no sense from a set theoretic standpoint. Does everybody see that? If I write this, this means this is like garbage. like this doesn't make any sense from a set theoretic standpoint if I'm talking about functions, right? Because now I'm talking about them like they're algebraic terms with variables, right? And this is very common in analysis to do things like this, but it's somewhat informal in the aspect that you would look at it like, okay, if this is supposed to be a member of some set, then surely I'm using it a little weird because now I'm talking about a set of functions and I'm adding it to another set of functions, and that's a little strange, right? So very often in an informal sense, though you can't always define it in its own way, is you can look at each of these and apply the exact same rules that I talked about. Like you take the highest order term, and then you could just write this all in terms of big O. So for example, I could say that this is all big O of n cubed. So this is meant to help you write things a bit more algebraically, but be warned, you're supposed to read it from left to right. Don't go right to left. This is not an equality. When I write this equal sign here, you should read it as is, not equals. Just to be very clear, this is not equals. It's just very helpful for simplifying calculations. So are there any questions about big O notation? So hopefully this gave you some fun insight about big O notation if you've never heard of some of these things before. I can always elaborate on more of these things if anyone has any questions about it. But yeah, we'll very often use this informal use in this class. So if you're ever writing up a paper that has algorithm analysis, typically people like using this equals-based notation, but you don't have to. But I must stress that if you wanted to be a bit more pure about all of this, instead of using what you do is you would take all of those and you'd essentially take them all together in terms of unions, and then you would posit and say that it's a subset of big O of n cubed. That's how you would write this actually in a set theoretic way, if you're curious. Okay, so if we're okay with that, let me proceed. I'm going to define a time complexity class to you. Okay. Okay, so when we have so we have to be careful. We have to be very careful. So this right here is just, it means is. It's not an equal sign, just to be very clear. So if you're saying approximately equal as in like, oh, it's plus some epsilon, and epsilon is a constant, then you can get away with just using that is notation like I have it here. However, you have to be very careful, because if, say, for example, there's this other term, like an epsilon that's some part of the input, then you have to include that in your expressions. So just as an example, you may be familiar with, like, if we look at graph algorithms, very often the inputs will involve the number of vertices and the number of edges. We often have to include those types of things in the running times if they're relevant when we're counting the operations. So if I have something like it's approximately equal to something else, we have to be a bit more careful. That's all I'm really saying. perhaps after you can always ask me about it. I'll be happy to elaborate further what maybe in this specific context. But yeah, this will suppress constants and all sorts of things like that. If you had like 1.44 times n, you can suppress that constant and then you could just get big O of n. Okay. Hopefully that clarified that a little bit. If not, you can always ask me about it after, okay? I'm very happy to answer these things. So now I'm going to talk about a time complexity class. This is going to be one of those really important things to pay attention to. Okay, so I'm going to define a time complexity class. So this is going to be very often how we're going to classify problems or languages for the remainder of this course. So we'll have a few different versions of this, but this is going to be generally one of the ideas here. I'm just going to broadly define it first, then I'll kind of narrow it down. So I'm going to let complexity function, that complexity function t, its name is going to be t, because t sounds like time. I'll make it non-negative, but it's okay if you make it a positive real as well. I may in the notes have it where it's a positive real, but it doesn't really matter with this context. We're going to define time, and time is all capitals like this. Time of f given input n to be a collection of languages or problems, depending on which context you'd like to talk about the languages, decidable by a Turing machine in big O of t time. So time for a given function, it will consist of all of the languages or problems, however you want to view this, that are all going to be solvable if you think about this in terms of problems with algorithms, to be solvable in this amount of time. So for example, if I wrote f here. This should be t. My apologies. Like I said, earlier on I was writing f. Let's write t. My apologies. So I have t. So suppose t, for example, was, say, n squared. Say it's quadratic. What this would be saying is time of n squared would contain all languages or problems that are decidable in quadratic time. That's what this would say. So just a couple of remarks that whenever unclear, we use d time. So instead of time, so I'll just assume that we're talking about a deterministic Turing machine. I'll use the word time, but if it's ever time where it's really unclear, I can write d time to talk about a deterministic, to say deterministic time, meaning it's solved by some deterministic Turing machine, or decided by one, just to be a bit more careful. And whenever we write n time, can somebody take a guess of what n time would be for? I'll tell you, n time, that's for our non-deterministic Turing machines. So just like D time is for the DTMs, this is for the NTMs, the non-deterministic Turing machines. So if ever I need some way of classifying the, yeah, exactly. Very good, very good. So we got enough time here to analyze the running time of a Turing machine. So why don't we do that? Because I feel like I want to make sure you see one proper example of doing this. This is sort of one of those things on my list of things I need to talk to you about. Is that I want to make sure you have an idea of how you're going to use these complexity functions to measure the efficiency of a Turing machine. Because I'm certain in your studies you've seen probably at least one or several examples, depending on what courses you've taken, of analyzing some algorithm using big O notation. But I have to show you how you do it with a Turing machine. So I got to do an example. So let's do an example. We're going to consider a previous Turing machine. I believe I called it T2, if my memory serves me correctly. For the language L is going to be 0 to the n, 1 to the n, such that n is greater or equal to 0. I believe this is what I had. If not, it's 1 here. And I defined and described to you a Turing machine that decides this language. So the transition diagram looked like this, right? So I had Q0. So I had my start here. Then I had it where when I encountered an A, I wrote it as an X. Then I had a state called QA. And if it sees a Y, it'll just not change the Y. If it sees an A, it keeps the A there, but it goes right once it's encountered an A. And then when it sees a B, it writes it as a Y, and then it goes left. And then I had QB. And I have a Y. I don't change the Y. If I see an A, I don't change the A. And then I go right back here, and I made it so that when I see an X, I don't change the X, but I move to the right so that I could read another A, right? Does everybody remember so far what I'm talking about? This was a Turing machine I showed you previously when I was trying to give you an example of one for a non-context-free language. And I showed you this basic example so that I could show you how you could do it for A to the N. Sorry. Yeah, 0 to the N, 1 to the N, 2 to the N, or A to the N, B to the N, C to the N. So we had it where we want to move all the way to the right by scanning it just to make sure. Q's, let's see, Q. Yeah, there's no arrow go. Yeah, so it goes Q0 to QA, then QA to QB, then goes the QB back to Q0. But there's no one that goes. Yeah, so it only. Ah, thank you. Oh, thank you. Yep, thank you. My apologies. It goes right. Thank you. Thank you. For some reason, I was just thinking edge for some reason. I was thinking about the direction of the... Yeah, so this whole process, remember, this is for just doing that sweep where we get a matching A and we try to find a matching B. And then we kind of sweep back and forth. And this will allow us to keep repeating that process. So I have QR, and then lastly, I had the final state, QB, right? Where I get to the blank. Oh yeah, and I also need to give you the direction on Y here. But yeah, this was the Turing machine I gave you some lectures back, right? So I want to measure the worst case running time of this Turing machine. So in this Turing machine, given input W of length n, we had 3 main stages. Which form the basis of our analysis. which form the basis of our analysis. My apologies. Okay, so the way I'd like to approach this is very often what you do with a Turing machine when you're analyzing the running time, is that you want to think about it in terms of the way you design the Turing machine. So very often when you're talking about it, you'll have like your zigzag process, for example, where you go back and forth, where you're sweeping the tape, for example, like here. Like this start here sweeping across the tape, right? So what I recommend when you're doing worst case analysis or computing the time complexity for a Turing machine is break it into stages like this. So we know, for example, there's 3 main stages here. One is where I try to get an A to match with a B, right? And then I have this process where I'm going to sweep back, right? I sweep back. But remember, when I do that, it causes me to repeat this again and again and again until I don't see an A, right? And then I do one final sweep across the tape. If any time there's a transition that fails in this process, it halts, right? So there's kind of 3 phases. So I'm going to do my analysis in the terms of these 3 kind of parts. The first 2 are going to be closely related, and that's actually where we're going to see our big O term really come out and shine. So an A is found, and at most big O of n, you see how I'm using the big O here, is I could be more careful and count how many times it happens in some worst case scenario. But by doing this, I've covered my butt to make sure that maybe it's like n-1 or something at some point during the Turing machine's process. It may be the case. But when I write the big O here, I'm suppressing those details when I use this. This is where the big O notation becomes very helpful when we're doing analysis with a Turing machine. When you're doing this with, say a pseudocode that's based on some computer programming language or just some general computer-esque language or one based off the RAM model, you very often will have it where you can explicitly count iterations and you can very much easily define what the worst case instance looks like. Here, it's a little bit like, okay, well, what if it halts somewhere else here or there? It may have a number of moves that are quite similar. This makes it so it's a little easier so I don't have to worry about, oh, it's going halfway across the tape, so I better put n/2 or something like that. This is why I'm using it in this way, and that's how I defined the big O notation, so I could get rid of those little details. But just be careful when you're doing this. Make sure you don't move too many details. This marker is being a little silly. Let me use a different one. And at most, big O of n moves. Moves are made to match this A with a B, where each is labeled X or Y respectively. So notice that by using the big O notation as well, I've also accounted for when it sweeps backwards. So like when it comes back this way off that loop, I've accounted for that in the big O notation when I do it this way. So it's very subtle. However, we have this second part that happens. Notice that if we failed to find a match between a 0 and a 1, a 0 or a 1, the machine halts. Presume otherwise. So this is me effectively laying out what's going to happen at most. Presume otherwise. That there are big O of n potential matches. that repeat step 1. Sorry, stage 1. That repeats stage 1. Now, if you want to be a bit more precise about it, it probably will be half, right? It'll be about half right down the middle. But notice that the big O of n will suppress those details. We don't really care about those kind of constants. So then there's lastly that final scan that happens right about here, right? A final scan from left to right on the tape. And to be a bit more precise, I won't write this explicitly, but remember, this will land us right at where there's going to be not an A anymore, but it'll land right on where there's a Y, and then it sweeps from the Y all the way to the right to the blank, right? So we go left to right on the tape, starting at the right of an X. Starting at the right of an X. Starting at the right of an X. At the right of an X, which scans no more than big O of n tape cells. Does everybody see that? So that's my final sweep that happens from the right of the last X that's going to appear during this execution all the way to the blank on the furthest right. Notice how the big O of n is being used to suppress the fact that I'm going to potentially have to go across half of the input when I scan those Ys. So now here's how we do the analysis. So these are my 3 pieces here. So here's a way you could go about this that's pretty slick. As stage 2 repeats stage 1 at most big O of n times the number of moves moves in total for stage 1 and stage 2. Can somebody tell me how many moves are there in total for stage 1 and stage 2? In terms of big O. Well, it's not n, but them together. Because notice that it does stage 1. This performs big O of n moves, but it repeats this n big O of n times, right? So it does stage 1 big O of n times. So how many in total should that be in terms of big O? It's not n. It's, what is it? I got a puppy dog crying. She's like, oh no, and I know the answer. N squared. It's n squared. Very good. Very good. It's n squared. Finally, stage 3. Takes at most big O of n moves. So the time complexity is, so time complexity of T2, let me just be a bit more exact, of T2 is, so I'm just going to write this all out by taking all the bits and pieces. So I've accumulated big O of n squared moves. And I have that big O of n moves that happen in stage 3. So this is big O of n squared. So anyways, With that being said, let me just summarize what class this falls into. So you can say, as a consequence of this, that L is in time n squared. And that's because T2 decides in big O of n squared time L. So I apologize for going longer here today, but hopefully you appreciated me just going a little bit longer here just so I could get those details for you. So I apologize for that. So that being said, when we come back, I'm going to start talking about the connection between computers and Turing machines with respect to time complexity. And I'll be talking about two very important computational complexity classes for the remainder of this course. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.